Okay, so here we are in lesson 4 of applications of exponential and log functions. Okay, so in this lesson we're going to solve log equations, and it's saying here that we'll either arrive at this type of equation, or the other one shown is that we'll arrive at this type of equation. In the first one, if this is the case, we can just, we delog both sides and we get p equal to q. In this case we can do drop, swing, bump, and p will equal b to the q. So this exploration is, maybe you want to try this before you look at it and let me know how you get on. So here's the exploration and the solution that goes along with it. I'm going to scroll up in a moment, but you may want to pause here just to look at it, and then I'll continue on with the lesson. So in the above example, basically it arrived at a quadratic and had two answers, and when substituted into the original equation, one of the answers did not work because it led to a negative log, so that was an extraneous answer, and so only one answer was possible. So note, when attempting to verify the solution x equals -2, we reach the situation of the log of a negative number. So we know that log expressions are only defined for positive values of the argument, so this is called an extraneous solution. Notice that this is not the notice that it is not the fact x is negative that makes the solution extraneous. It's the fact that the argument of the log is negative, what was in brackets, in other words. So we can't take a log of that because that would have been negative. So let's go into solving log equations using the law of logs. Log expression is defined only for positive values. When we solve a log equation, it is essential to verify that the solutions do not result in the log of a negative number, because then that would lead to extraneous solutions, or solutions that are not valid. Values obtained by solving log equations may be extraneous and must be verified, so back into the, whatever answer you get, back into the original equation. All of the arguments of logs must be positive. Whatever you're logging, in other words, must be positive. If the base is a variable, it too must be positive. So note this and this. Alright, example 1. Solve the following log equations. Well, log x squared equals log 16. That is, you're logging two separate things. There's nothing in front here or here, so we can actually just delog this and write x squared equals 16. So in that case, x would either be plus or -4. So those two answers need to be verified. Obviously, if you put 4 in here, you square it, then of course that's okay, or -4, as long as you square it, gives you a positive number, so you can log that too. So even though you're using -4, you're not logging -4, you're logging the square of -4, and that is positive. Part 2, 2 log x equals log 16, so this is where you bring the 2 up, and then you get the following, so then you can delog, so x squared is 16, and you get the same result as before. Now let's try putting in our values. We get 4, we're logging 4, that's okay. What about -4? We log -4, no, we cannot do that. So this is the original equation, and you're putting the answer into the original equation, which, if you take the log of it, does not work because it's a negative log. So only one solution in that case. So, and we've come across this before. When we square, then x can be positive or negative. Remember, we had these type of graphs. Whereas for this situation, we only had the one side where x could be positive. So that's what's going on there. Alright, example 1. Solve the following log equations. Oh, we just did that. Yeah, this is what I was just explaining here. Part B. Solve the equations in A using a graphing technique. Illustrate the solutions on the grids provided. So here the solution, we've basically brought the log 16 over together, and we're looking for when this, I guess, equals 0. And we can graph both of these, and in this case graphing both of these, and we're looking for when this equals 0 because we brought this over to the same side. In other words, this here has been brought over to this side, so this side now equals 0. So notice when this crosses the x-axis, when y is 0 in other words, we get a value of 4 for x. In this case we get two values, -4 and +4. And then in part C, explain why the solutions to the log equations are not the same, even though 2 log x can be written as log x squared, simply because the domain of log x squared can be all real numbers as long as x is not 0, but 2 log x has to be greater than 0. Example 2. Solve for x in the following equations. So really what we're trying to get at is probably either a log on one side equaling a number on the other, or a log equaling a log. So we basically are trying to rearrange this equation into something a little bit simpler. Notice there are 1, 2, 3 logs in this equation. Well, in this case we know a log minus a log can be written like this. We can even bring the log 8 over if we need to, but they're both base 4. And in fact, at this point, we've got a log of something and a log of something. We can delog and write the following. So then just a bit of algebra will get you your solutions or solution. And so in this case, we end up with this expression here, multiplying with the brackets. There's no x squared, so it's not going to be a quadratic. Basically simplifies to 25 equals 15x, or eventually to x equals 5 over 3. Verify this in the original and make sure that if you put 5 over 3 for x, that you're logging something that's positive, and in this case it works. In the other scenario over here, we have a different example. We have a 1 here, which is not a log, but if we really wanted to write this as a log, we could write it as log 6 base 6. And I don't think they really use that technique here, but what happens is they bring the 1, leave the 1 alone, but bring this log to the other side. So here we have it right here. In that case it's a log plus a log, so we can write a single log, multiply these two brackets together, still equal to 1 on the other side. And now we can do drop swing bump. The brackets drop down, the 6 swings over and bumps 1 up, so we get this here. Okay, and then we could file this out, bring the 6 over, and then refactor this into the following, and we get x equal to -1 or -6. Make sure you verify these two, and -6 does not work because -6 in here will make the bracket negative, so you can't log a negative number. Only -1 seems to work in that particular case. Example 3. Solve the following. We could use the same technique, basically bringing the 3 over to this side. It's a log minus a log. Bring the 2 above, bring this up here as well, and then you will get the following. You can combine this to be 1 log with the x squared here, and then you can do drop swing bump, leaving this part here, and so then you can do a little bit of algebra or cross multiplication. X squared times 1 equals 3 to the 3 times the x plus 3. So you end up with a quadratic equal to 0, which does not factor, or even if it did, you can still use the quadratic equation, quadratic formula rather. In this case, since it doesn't factor, The reason it doesn't factor is because this b squared minus 4ac is not a perfect square. So when we square root this, we're actually going to get a decimal. And there's two values, and we have to verify both values. And the negative will not work because negative 2.7 does not work in here in this part of the original equation. So only one value is possible. Let me scroll down here. Okay, so it says here we're solving more complex log equations. Number 4, solve this equation here. Well, there's a log within a log. Not to worry, let's have a look. It says solve here by twice converting to the exponential form. So I would imagine that we can do drop, swing, bump here. If we drop this whole bracket down and swing the 2 over, we can write that in this form here. So fair enough, we've done that, which equals 2, and again do drop, swing, bump, bring this bracket down here, bring the x over, bump the 2 up, and then it looks like a quadratic, bring everything to the one side. This factors, luckily enough, and we get two values. Are they any extraneous? Well, checking 4 and negative 4, 4 and negative 1, the negative 1 is not possible simply because we've got log of a negative base. This cannot be negative. So only 4 will work. Oh man. Okay, let me just pause the equation here, the video here, and make two parts.